Dobré ráno, děkuji za několik řešení pole, která ta řešení mi chodila různými kanály, tak je budu muset všechny pohledat. Vím, že někdo to posílal přes Teams, někdo to posílal e-mailem a že jsem jich obdržel alespoň 5, ale teď bych to úplně neuměl, takže já ta vaše řešení vezmu, vezmu je na jeden počítač s nainstalovaným MATLABem a budu zkoušet, jak rychle běží. Slíbil jsem, že já vám dnes ukážu nějaké triky, jak to rychle naprogramovat. Já jsem se do těch vašich M-scriptů ani C-čkových programů nedíval, takže vím, že jeden z vás mi napsal docela dlouhé povídání o tom, jak by se dalo dělat jinak a podobně, ale já se teď podívám, já vám řeknu to, jak to mám naprogramované já a třeba budete i rychlejší, uvidíme. Kolega Trávniček odpovídá, tak já se pám ještě do chatu. Emil Tyvoňák byl odebrán. To mě podržte. Kdo mi zasahuje do týmu? Dobrá, tak pardon, já se pokusím připojit Emila Tyvoňáka, to je opravdu zvláštní. Takže
Dobrý den.
Pardon, vy jste kdo?
Tyvoňák, konečně jsem znova dostal.
Aha, tak to já... Dobrá. Well, is there anybody talking only in English present?
Yes, me.
Well, okay, then speak up. Thank you. So we switch into English. Sorry for the inconvenience. And let's continue with the lecture. It seems that now we are ready to do so. So I will show you a few tricks which can make the calculation with finite differences a little bit faster. By a little bit faster, I mean possibly even 50 times against a brute force code. A brute force code is something that you program just without thinking. It works, just it runs a little bit slower, which the problem is that for small problems it is not a problem. Once you get to bigger problems, like for example this problem we are attacking in 2D is an n raised to third order problem. So if you make 2 times more slices in one dimension, then there is 2 times more slices in the other dimension, and you need at least 2 times more passes through the net to get convergence. So by making 2 times finer grid, you get approximately 8 times longer computation. Not looking to the problem of memory considerations. So now how to do the calculations as fast or as possible, or at least faster. First, we work with a computer, mostly with PC. And the PC has an architecture which has a processor, and this processor is more or less built for 2 kinds of numbers. From 83, 86, that was the last processor that has not a coprocessor built in. So 486, Pentium, and all that stuff has a coprocessor, numerical coprocessor inside. And the coprocessor is capable of handling floating point numbers fast. But anyway, this fast is not as fast as handling integers. Now, since, let's say, Windows XP, so let's say that for last 15 years at least, we have processors with the bus and the arithmetic unit, which is at least 32 bits. Now, 32 bits in integer means a very large scale of numbers. 16 bits was 65,000 more or less values. Now this if you have 2 times more bits, you raise this to the second power and you get the number, the span of numbers you can represent exactly. But that's not only the point. The point is that such numbers are added, subtracted, and in some cases even multiplied in one clock cycle. So that is something which is very fast, and you can do that. Now, the second point is that you have to somehow handle division. I will just like first to set up a short consideration. So instead of handling floating numbers, which are difficult to handle, well, not that difficult, but long time consuming when considering divisions and multiplications, we will use integer. But of course, in order to handle our potential with sufficient precision, we will use integer, but in fact what we will do is fixed point decimal arithmetic or something like that. So we will say, okay, instead of potential equivalent to 1, we would consider a potential equivalent to, say, 1 million. Now this is a good precision, so we will represent 1 as 1 million. Still, during that calculation, we would need to add 4 numbers, and that should not overflow. But 4 millions is well within the range. So okay, we have enough space. We would even get a correction which we will multiply by 1.5. But still that would be in the range of the integer. So we could handle 1 million instead of potential of 1. Now this is good because the integer value would run much faster. A short note, today we have 64 bits in most of the computers, whether it is desktop, and if you consider your, let's say, your mobile phone, there is something like ARM processor, which again handles integers in one clock cycle, at least addition and subtraction. So now we have saved a lot of time by changing the representation. We use integers and that's faster. But this is not the only point that lasts. The second point when you have access to a compiler is that mostly a compiler generates a foolproof code. That foolproof code, in fact, checks whether your calculation gives a valid result. For example, whether there was not an overflow. And this is not as fast as can be. We have now the representation where the maximum number we can get is 6 million, but that's much less than you can handle with a 32-byte integer. So you can never get to overflow. You can never get to underflow. So what you can do is to switch off overflow checking. And that speeds again the computation. That's something you possibly cannot do in MATLAB, but you can do it in a C++ or C or Pascal compiler. And third, there is one problem which slows the calculation now more than the calculation itself. That's a difficult sentence. So what I'm talking about, you have always 4 numbers, the neighbors in the neighborhood of the point you are currently updating, and you have to add them, and then there are some subtractions and so on. But in order to add those numbers, you have first to find them in memory, or to use a correct word, you should address them. And now there was a problem with computers like your mobile phone or a PC, those computers do have linear memory, linear addressing. So in fact, they have a vector of addresses. The vector is today very long, but still it is a one-dimension vector. So you have address, sorry, I will do only 16-bit address because that's enough. A short address, so we have the address 0, and you have up somewhere upstairs, you have F hex. But in this calculation, you have a two-dimensional field. So the two-dimensional field must be somehow stored in that memory so that you can access it. And what compilers do with that is that they use something which is called mapping function. Some compilers store a matrix so that it stores. So the mapping function does this. We have a matrix, and in order to get it into a linear memory space, we cut it. We could cut columns so that this column would go over here and have the first column. Then there is the second column, and we get it just on top of the first column. And in this way we can map the whole matrix into a linear memory. Some other compilers may do that into rows, so that they get one row and put it there. Anyway, it has some mapping. Now, during compile time, you would get the address of the beginning of the array in the memory. So let's start, this was 0. So in fact, if you try to access any of those numbers, I mean, you can read it or you can store it. Anyway, there is quite a complex calculation behind. In fact, what the computer does is it has a calculation like starting address plus, then you get, let's say you have something like A, I, J, which is the array element with the index I and J. So now there would be plus. Let's get it in the case that we store columns by column into that thing. So first you would have to take the number of elements, the length of one column, and you will have to take j minus 1 times the length of a column. Now, plus I minus 1 times the length of one variable. If you store, for example, a 4-byte integer, most computers can address any byte, then you would have there the variable length. Some computers have the addressing only in the bus width, then this would be simpler. But anyway, in order to get any of those elements, you would have this, 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 and this. You have to fetch it into the processor, and then you store the result. You would first have one addition, one decrement, one multiplication, second addition, second decrement, and second multiplication. which is a process. So you originally had 1, 2, 4 adding operations more or less, and in order to access one of them you have something which is much longer because multiplication takes more time. So in fact you are mostly, if you have a brute force approach, you are mostly searching in memory or mapping the memory, and only sometimes you do a useful calculation. In order to get rid of that, you might somehow use simpler memory allocation. Well, first what you can do, at least it seems you can do that, you could write a program that would write a program which would not use an array, but for example variables like a, o, o, 1, o, o, 7, which would stand instead of A17. If you have those variables, the computer would assign each variable, or the compiler would assign each variable a value, and then it would create a very effective code. But you would not use cycles in that, you would just write a long code for the solution. For each of the points you would write a special piece of code. That is possible to generate it by machine. The problem is that most of the compilers have internal stacks and would run out of space with 1 million of variables. So you would have to test it, because unfortunately many compilers do not report that they ran out of stack, and they generate nonsenses then. But anyway, this would be the fastest possible code. Of course, you might also write that in a machine code, which is the fastest way, but not very nice to do. So how to address the array more effectively? Well, first you possibly should not use a construction of a square array. Now, it depends on programming language. I would use Pascal syntax, but anyway, you would possibly understand it even if you use another language. So I can define the array in several manners. For example, I can define like type A is an array one to n of integer, for example. This is nice. This is simplest to handle. I can then write aij as an element. It's quite easy to debug that. But on the other hand, it is slow, as I have shown. So what about making a bit more complex construction? For example, I will first make type B, which is an array one to n, of course of integer, but now I have defined a vector, and I can define the array as an array of vectors. And in order to access it faster, I can do it, for example, in the manner that I define type P, which is a pointer. Sorry, it's not an arrow. Pointer on B. Well, what's the fun about using a pointer? Then I can define a type C, which is an array 1 to n of p. So now I have an array of pointers, and instead of writing aij, I would now have to write, I will now mix, I will use C, which is now a type identifier, as a variable identifier, but let's make it simpler. So I could write C I J. A little bit more writing, but now I look into the array C. I only map once. I have directly a pointer to the row, and then I address the element J. And if I make some tricks with it, I can set one pointer to the upper row, one pointer to the middle row, one pointer to the lower row, and then I only get this value, this value, this value, and this value from one-dimensional arrays. Now, I know that I have already read this and this value in time, so I make the calculation, put the result there, and continue. But I have the result already in my computer, even in my mathematic unit in my processor, so I should not read it again. And with this, I can get much faster calculation, because if I have a row of 1000 elements, I only update the pointer after I run through the whole row. Then I'm elaborating this row, so I make this pointer shift there, this pointer shift there, and read a new pointer to the next row. And with this, I can make, let's say, 2 times speed up. The important point again is to switch off any checking of overflow, underflow,